Our paper is called Developing an AR-based tool for teaching motion analysis on assembly tasks. The authors are Nicolaus Angel, Horst Oscholit, and Jose Garcia from the University of Applied Sciences Technikum Wien in Vienna, Austria. We are part of the Department of Industrial Engineering, where we prepare students in engineering courses. Our Competence Center integrates technologies in our teaching courses. Those technologies allow to simulate or visualize concepts and processes. Augmented reality, or AR, is one of the technologies we are integrating in our courses. It is always a question whether an implementation in AR will be applicable to the educational and industrial settings. The question in this case was whether use of AR could help achieve better results in explaining the complexity of an industrial assembly task. Small production batches of different products demand highly skilled, well-trained personnel who often experience a high mental workload. One way to address those workloads in manufacturing processes such as assembly tasks is studying actions of movements. This helps to understand the requirements of carrying out an industrial task. This work looks at predetermined time standards and specifically at modular arrangements of predetermined time standards, or MODAPs, to analyze an assembly process and assess how the use of AR can help integrating it in education and industry. An additional question was how will object detection work for the purposes of training in MODAPs. There is an increasing number of AR applications targeting industrial training. Some technical challenges still limit a wider adoption of AR for supporting industrial manufacturing processes. To display the virtual content exactly at the corresponding spatial position while moving the AR device, the real environment needs to be captured and tracked relative to the device and the user. Markerless AR systems are likely to become the preferred tracking type used in industrial settings. Therefore, it was important to investigate its application to our selected scenario and problem. A testing application was developed in Unity and implemented for desktop PC and for AR using Vuforia. The application provides augmented instructions for the person carrying out the task. To display the virtual content exactly at the corresponding spatial position while moving the AR device, the real environment needs to be captured and tracked relative to the device and the user. Two methods for object recognition are used in the application based on PTC's functionality, Model Target and Model Target 360. The participant will be following the instructions and is expected to complete the process quickly. The application has a minimal user interface since it is just aimed at providing written instructions while the user can see the parts required for the assembly. The modular arrangements of predetermined time standards model proposed by Alkan, Vera, Ahmad, and Harrison was used. An interesting part of this model is that it considers operational complexity. The operational complexity measure integrated in the model considers function of physical and cognitive efforts as well as quantity and diversity of operation-related activities. The sources of complexity in manual assembly operations considered in the model include product-related factors such as material, design, and specification for each part or subassembly within the product. It also considers process-related factors, for example, effects induced by selected assembly methodology, sequences, and volume requirements, as well as the effects of product variation, operational uncertainties, process deficiencies, or insufficient work instructions. Personal factors consist of several elements which affect the perceived complexity by the operator, such as mental and physical capacity of the operator, his or her training level, corresponding manufacturing knowledge, personality, culture, or motivation to work. Additionally, the model accounts for environmental factors that affect the performance of the human operator and comfort of the assembly task, for example, workspace ergonomics, heat stress, or available physical space. The application guides the user through an assembly process. It records movements that can be analyzed. As such, it is capable of providing detailed movement analysis that will be difficult to achieve in another way. A video application records all the user movements based on tracking their wrists. Among the results, we could see that the time to carry out the assembly and number of errors were two main metrics, and the possible errors were classified in two categories: grave errors, such as incorrect use of the tools, and critical errors were actions which resulted in a malfunction or non-usability during the assembly. A limit of 20 maximal critical errors was established for each condition for all participants. It was expected to see a difference between the use of paper-written instructions and instructions on device, and it was surprising that the difference in performance between tablet and PC was not higher. Our implementation showed that the ModApps is a useful but complex model to get insight into assembly activities, but AR offers a useful alternative to make those concepts clearer to students. We intend to explore other scenarios featuring additional industrial processes associated with mechatronics. Thank you very much for your attention, and if you have any questions, please don't hesitate to contact us.